Okay, what's up? It's Miss Gabriel here again, presenting yet another part of a chapter to my lonely old computer. So this was a pretty intense chapter. Again, I know it's going to get easier, I promise. And I know it was really hard to learn all of this for the first time in class. So I'm just going to review and summarize only the high points. And hopefully you can put it all together. If you have any questions about it, just ask me during homeroom or after school. So we're not going to go into biomes yet for this video. We're just going to go into the unequal heating of Earth. So remember that Earth has 5 layers. We'll talk about those layers. We'll talk about what causes the unequal heating. And we'll talk about what we've already spent a whole lot of time with in class, the effects of seasonal differences in temperatures. So in class, we actually created, well, we played with a model to really demonstrate the effects of the Earth revolving around the sun during the year. Now, things that you really need to take away and remember are that Earth is always tilted on an axis of 23.5 degrees. The orientation of that axis, at least in your lifetime and many generations to come, is always going to be oriented in the same direction. Yes, Earth wobbles, but you don't need to know that for this class. As we go through the seasons, which we also practiced and modeled again and again in class, remember we're looking at around every 3 months. So March and September are our fall and autumnal and spring or vernal equinoxes. Equinox means equal day, equal night. And June, which is summer, and December are considered our solstices, which is for December our shortest day and for June our longest day. We modeled that in class. Some of you drew this in your notes, and we talked at length about what this should look like when you're taking notes in your notebook. So remember, in your notebook, you should not just be copying the diagrams as you see them. You should be interpreting the diagrams, then reading the paragraphs, then listening to me in class, and then adding to and modifying the diagram in order to understand it more deeply and make those connections. And we really did a lot more in this with this diagram than what you see here. So remember that the rays of the sun do not always beat directly onto the equator. When the Earth is oriented in the June solstice direction towards the sun, the rays are more directly over this dotted line, which is the Tropic of Cancer, and 6 months later, Earth is still oriented in this direction on its tilt, on the axis. And that's important. The axis is what allows the sun to change its intensity or appear to change its intensity as we revolve around it. So now it's on the lower dotted line, which is 23.5 degrees below the equator, the Tropic of Capricorn, which means this hemisphere of the Earth is getting more solar energy, more intense energy. Before we go into all of this, I did remind you of something you should have learned in middle school. Most of you did not copy any of this information down because you probably thought you know it. But remember, when you're looking at the book and you're listening to me in class, we're preparing for and practicing for multiple choice questions. So if you look at something like, oh, this is what weather is and this is what climate is, remember that you want to start thinking about, because look guys, let's be honest, it's an AP class. AP class is all about getting the college credit, which is all about getting a really high score on the actual AP test. So if you're given a test question about what weather is or comparing weather and climate, the kinds of things that they might ask you are, okay, weather is all of the above except one, and you have to pick which doesn't belong. So remember, the climate is always going to be average weather over several decades, not just one season, not one winter. We may have had a cold winter. We may have had a cool summer. That's not climate. Climate is the average of those little seasons over several decades. Then in your book, you saw like all these definitions and descriptions of layers of the atmosphere. What you shouldn't be doing, as I've been teaching you again and again in class, you should not be copying all these definitions. Make graphic organizers. Organize the information in a way that reminds you so that you can think about what you drew. So they gave you a nice little fancy diagram in the book, and we talked at length about this troposphere and stratosphere in class. Look for the patterns, write the patterns down. So here are some examples of like things that you could have taken away from the textbook. The density of air is going to increase with altitude. That's not clear in here, but you should say that around this. Temperature increases in the stratosphere. Look, the temperature is increasing. You know that. because the sun's UVB and UVC rays are warming the upper part of this layer. Ozone is in the stratosphere. Now, I really emphasized in class, the ozone in the stratosphere is good ozone, good ozone, good ozone. And what is ozone? O3. We have ozone here in the troposphere that's actually a secondary pollutant, and that's bad because ozone actually, it's still O3, but ozone is a respiratory irritant, and plants don't like it either. So ozone in the stratosphere is good because it protects us from this radiation, and by protecting us from it, it actually protects us from cataracts and skin cancer, which we'll get to in another chapter another time. So these are the highlights of these important ones. So the troposphere is where all our weather occurs, and the troposphere is where the temperature is constantly decreasing. And we don't have a big orange line in the sky that says, oh, but now you have entered the stratosphere. No, 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 no. And it's not always at exactly this location and this altitude. It's going to vary based on several different factors we don't need to get into. But how do you know that you are now entering the stratosphere? Well, weather balloons are tracking the temperature changes. And you're going to learn in the next few slides, clouds are not going to form as much at all when the temperature is increasing. So our clouds and our weather are really happening where the temperature is decreasing as we increase in altitude in the troposphere. And the stratosphere, all it's really good for as far as our class goes is this ozone layer, the good ozone in the stratosphere. So now what you should do is you should think about the diagrams you have in your text. You should cover them up, and you should do this throughout while you're studying. Cover them up, and then give yourself a quiz. Ask yourself, what are those layers of the atmosphere again? What were they good for again? See what you remember, and then uncover with your hand. That's how you study while you read and while you take notes. And that's how you review. Cover it up, quiz yourself, check. Cover it again, quiz yourself again 15 minutes later, check. Okay, so these are really important things that I'll get into, but we're going to talk about right now the angle of the sun's rays. So the angle of the sun's rays I already talked about in the first diagram strike differently on the Earth depending on the Earth's position as it revolves around the sun and the angle of the rays. So not only do you need to understand the diagram, but you need to be able to articulate the information of the diagram in words that make sense. So you should look at the diagram, you should cover any of the words in the book after you understood it, and then you should try to repeat that information, because 40% of your exam is going to, who knows what kind of questions you're going to get, but 40% of it is going to be essay responses. And you may be asked to explain things like this. And if you can't use this verbiage in your explanation, you might not earn the points. So understanding it is great, but being able to explain it is the highest level. And that's what they want to give you the college credit for, if you can do that. And then I'll show you some more, and we're going to talk about albedo. And albedo is just about that reflection. So starting with the angle of the rays. So if the rays are striking more perpendicular, we're going to get a higher intensity. If the angle is more oblique, then the rays are spread out. It's almost like they're less concentrated. And that means this whole area is getting less energy. That makes sense, right? That causes a difference in the heating of the Earth at the same exact time. Now, if these direct rays are when the Earth is in the vernal equinox, which is spring, or in the fall equinox, then we're going to still get a different area, which will cause differential heating. And then as the Earth revolves around the sun, the size of the area is going to change. And I know that makes sense to you. Okay, so albedo, all it is just reflection. But the fact that, like blacktop, absorbs a whole lot of that sun's energy and it reflects very little of it, you know that it does. This has a low albedo, blacktop. So you go to the mall and it feels warm around the mall. You go to a city, it feels warmer in the city than when you're in the suburbs on the same day. Why? Because the city has a whole lot of low albedo surface material. So that means it's absorbing more of the solar energy and it's reflecting less, and it's going to be warmer. It's going to be warmer here. Now, of course, it doesn't just have to do with like the color of whatever that surface is. It also has to do with the material that it's made out of. So like water Water can have a low albedo, but it also can have a high albedo depending on how much energy it's absorbing, the temperature that it is, and the intensity of the rays. And clouds also can have a pretty high albedo or pretty low, depending on the type of cloud and how high the cloud is in the sky. So this is important because this is another reason that surface of Earth is unequally heated, and that unequal heating is actually it's a good thing. So remember that high albedo reflects more radiation. So when I walked around and I talked to each of you individually about your homework, I saw that you wrote this diagram, but I didn't see that you wrote down the patterns. You didn't write that there's a high albedo here and there's a low albedo here. You didn't write that kind of stuff. So that's the things that are going to help you kind of remember and see the patterns so that you don't have to memorize anything. Remember, we're trying to read to understand. If we read to understand and we listen to understand and we talk to understand, then we don't have to memorize. All right, so what are the three major causes of unequal heating? Albedo, the variation in angle at which a sun's rays strike, which we practiced here. You remember that? You guys really like that thing. And the amount of surface area the sun's rays are distributed. Sun's rays. Okay? Okay. So what were they? Now I'm going to go back to it real quick, but that's the type of thing that you should be covering up, pausing videos, pausing your note-taking, pausing your studying, testing yourself and seeing if you can repeat it in your own words. And it's not about memorizing, it's just about understanding. And once you understand, you remember better. It's just a deeper level of trying, guys. Okay, so we just practiced this. Your Mod 9 answers we went over in class. And then I have to go into air currents. You sticking with me? I hope so. Okay, so we have four properties that influence the movement and circulation of air. Do you remember what they are? Well, I'm going to go over them. Density. What about density? Less dense air is going to rise. It's just like buoyancy. You learned it in elementary school, except we're talking about air. I mean, it's slightly different, but think about the labs you did and things that float and things that don't float. If it's less dense air, it's going to rise. Now, that's going to matter because we're going to talk about all the things, the characteristics that make air rise besides its density, like what makes it less dense, what's going to make it sink. Then we have water vapor capacity. Now, this is about forming clouds, okay? So I'll talk about that in a minute, but warm air, you know this. If you know this and you just remember water vapor capacity, this is going to help you. Warm air can hold more water. It has a higher capacity for water vapor. Cold air cannot. Now, I went over this in class. I told you to write this little clue down so that you could remember it better. So next to where you wrote about water vapor capacity, you should have written something like summertime is very warm. It's humid. It feels wet and humid out. Wintertime, where we live, is very dry because it's cold air. Cold air cannot hold as much moisture. So this chart is actually just showing you this thing called a saturation point. That is this mass of air as the air drops in temperature. So we're going to go through this line, okay? It can hold its water vapor only until a certain temperature. So if the temperature of air in the water vapor fell from 30, right here, from 30 degrees to 10 degrees, then we're supersaturated. This is when clouds form. Okay, so then we have this thing when air is rising and when air is sinking. That's called adiabatic heating and cooling. So what I did when I tried to take notes for the very first time on this, it was too much to read all those paragraphs. I took the bare minimum out of those paragraphs and I made like a little sequence chain. Adiabatic heating, the air rises. When air rises, because of the properties of the atmosphere, the pressure decreases. So the pressure in that air is going to decrease. Because remember, as we move up the troposphere, then the air expands. Now that is because the pressure decreases. So now the air mass is expanding. So if you think about a balloon that's rising, the pressure decreases in the atmosphere around the balloon. Then the balloon is going to expand. and then we get a decrease in temperature. Or the air can sink. If the air sinks, as this air sinks in the troposphere, pressure increases. You know this. And the air will decrease in volume because it's getting smushed. Think about that. And when that happens, it's just basic laws of physics. The temperature raises. The temperature rises. Now, latent heat is when the water vapor that's in that air mass condenses into liquid water. Okay, so we have water vapor around us. It's always 50% humidity, let's say, in the classroom. If the temperature starts dropping significantly, the water is going to be supersaturated in the air. The air is saturated, sorry. The air won't be able to hold the water anymore. The water will then condense onto things in the classroom. The water vapor in the air will condense into things in the classroom. When that happens, energy is released. So this is the opposite of evaporation that converts to water vapor. Energy is released, not energy is absorbed. So when condensation occurs, energy is released. This is called latent heat, this energy, latent heat. This happens when air masses are rising to form clouds, which I'm going to go over with you. So this right now should just be a big like, what? Well, actually it shouldn't because we already talked about it in class. So whenever water condenses, the air will become warmer. And because it's warmer than the air around it, it will rise because it's less dense. And then this happens again, which makes it warmer again, which makes it rise until they even out. Okay, so I just talked about all these things. And saturation point, remember, was just that water vapor. It's how much the air can hold at the temperature that it is. Okay, then we go into convection currents. So like all that stuff that we just learned, all these big words, and there were a lot, and it was pretty intense. All of that is really important when we talk about convection currents because convection currents are happening because of the sun's direct energy on our planet. So you just listen to me talk about adiabatic cooling as something rises and adiabatic heating. Now notice here it's showing this in this diagram, it's kind of showing it in a circle. So it's almost like a cell. So this is almost like a convection cell, which is something we're modeling in class, and we've been spending some time trying to understand this. But remember, we have humid air at the surface. It's slightly less dense than the air over, to its right or left, which is going to make it rise. As it rises, adiabatic cooling occurs. Then it reaches its saturation point because of it. Then clouds form. Clouds only form, I repeated this a million times in class, when the air is rising. When air rises, has met its saturation point, and the air condenses. That's when clouds form. And by the way, the condensation is happening around little condensation nuclei, which is just little pieces of dust all over the atmosphere. So then when the condensation occurs, remember that latent heat is released, and this cycle will continue until the air mass actually matches the surrounding temperature. So this air is going to get displaced by the other air that's rising. It's got to move out of the way. It's moving out of the way because there's more air coming up. When it moves out of the way, it's cooling, and that cool air is now dry air. So it's moving out of the way, and it's sinking down, and we'll talk about because this air is going somewhere. It's going whoop, right back into this cell, or it's actually going into another cell. So the air doesn't leave an empty void, an empty vacuum of no air around. Now this air that's up at the top, this cool dry air, it's more dense, it's going to sink. Now sinking air warms. That's adiabatic heating. And air that's sinking and warming does not form clouds. This is higher pressure. Sinking air does not form clouds because this is cool and dry air. So anytime you hear something about high pressure is cooler and drier air. You're going to have clear skies because clouds only form when we've got lower pressure of this air that's moist and that's rising and it's less dense. Clouds form over here, adiabatic cooling, latent heat release. Clouds do not form over with the adiabatic heating. I know that was intense, so you should pause and you should try and draw your own picture of it, use those words and explain what was happening there. That was intense. Okay, so now we go into, we're going to start with the Hadley cells. And I actually have a couple videos just to clarify this for those kids that are kind of struggling with this. So first, just kind of pay attention to what's going to occur in this animation. I'm going to show you a Hadley cell circulation. So just pay attention to what's happening. So we have rising air at the equator. The reason it's rising here is because the sun is directly beating here on the equator. As the Earth, moves or revolves around the sun, this little Hadley cell, the center of this Hadley cell, could be a little more to the north or a little more to the south. So we have rising warm tropical air, okay? It's rising air and it's tropical. So that rising air, because it's warmer, that's why it's rising too, okay? So it's rising because it's less dense. And then we just talked about all this cloud formation and why that's happening. And then this air is getting moved out of the way by the other rising air. And then it gets cool and it starts sinking. Now on our planet, that's happening at around 30 degrees north and 30 degrees south latitude. These are called our Hadley cells. This is one of the ways that the atmospheric circulation is happening globally. So it's low pressure here at the equator where the air is rising. We get a lot more rain. But remember what I told you happens right here at these high pressure zones, H and H, sinking air, high pressure, no clouds. What type of biome do you think you would find where it's just dry air all the time? It would be like a desert. And what type of biome would you find where there's low pressure and rain? You'd find like tropical, okay? It wouldn't be desert-like. So then we're going to add our winds. So these are just winds that have occurred because we have this high pressure. The high pressure moves into lower pressure. That's just what happens. It's another law of physics. So high pressure is moving into low pressure. By it moving, honestly, this wind would be going directly from north to south, but we have this Coriolis effect, which I'll get into in a moment. So this wind is being deflected because of the Coriolis effect, but it's coming from the northeast and moving right into that lowest pressure. And on the southern side of the equator, in the southern hemisphere, the high pressure is moving into the low pressure. And remember, the high comes from the bottom of the Hadley cell. So the Hadley cell is sinking air, high pressure. So the air is going to constantly be moving it's trying to move into a state of equilibrium. Okay, so it's going into the low pressure. It's coming from the northeast. It's coming not just from the north, but the northeast. And it's not just coming from the south, but the southwest, east towards the equator because of the Coriolis effect. Now, in addition to the Hadley cells, we have Ferrel cells and we have polar cells. So I'll get into that in a little